Today we are going to look at quadratic inequalities in two variables. The last few classes we have been looking at quadratic inequalities in one variable. So what happens when we have two variables? Well, just like inequalities in one variable, for example, if I look at x plus 3 is greater than 0, I can say, well, there's a whole bunch of x's that satisfy this. It is when x is greater than -3. We have the ability to isolate the x. And we have a one-dimensional solution, or in other words, we have only one variable to solve. So when x is greater than -3 is my solution set. But if I gave you x plus 3 is greater than y, instead of actually giving you a value, I said it was y, well then there's a whole bunch of xy pairs that follow that solution set. Right? If I plugged in 4 for x and 10 for y, that would work. If I plugged in 4 for x and 9 for y, even all the decimals, etc. So when there were two variables, we had to graph this inequality. We had to graph y equals x plus 3, right? Using a dashed line because it's not equal to, and then we had to test a point. So 0, 0. If I plug in 0, 0, is 3 greater than 0? Yes, it is. So all of those points are the solution set. So it is a region. So when you have two variables with an inequality, you have to graph your solution set. It has to be a whole bunch of xy pairs that balance that. Okay? So here we are with our inequality, or quadratic inequality. So we have a power of 2. So this is a parabola. If I change this greater than to equal, we have a parabola that is in vertex form. So I can see my vertex is 4, -2. So I can plot my vertex. 4, -2. My a value is 1, so it opens up. So when it opens up and the a value is 1, we go over 1, up 1. On both sides, we go over 2, up the square of 2. We go over 3, up the square of 3, which is 9. 4, 5, 6, 7, 8, 9. Etc. And so now we have where y equals, when all of the xy pairs that make the equal true. But we want greater than not equal to. So since it's not equal to, just like before, we use a dashed line. So we're using a dashed line for a border. This parabola, just like our line, separates our solutions to our non-solutions. So we have to figure out, is it inside the parabola that is a solution, or is it outside the parabola? For example, if I chose 0, 0 and plug this in, is 0 greater than -4 squared minus 2, which is 16 minus 2, which is, no, that's not true. So outside here is not the solution, so inside is the solution. So any point inside that region is the solution to this inequality. Let's try another. Y is less than or equal to -1/2 x plus 4 squared. So if I have, again, my equality, my equation, which is a parabola, and again I put it into vertex form. So my vertex is going to be -4, comma, and whatever is added afterwards is my vertical translation. So left 4, don't go up and down. So -4, 0 is my vertex, and my a is -1/2. So when a is negative, my parabola opens down. When a is 1/2, instead of going over 1, down 1, I now go over 1, go down 1/2 of 1. Instead of going over 2, down 4, I go over 2, down 1/2 of 4. Going over 3, I go down 1/2 of 9. 4 1/2, there we go. So, I've plotted my parabola. I need this to be exact. I cannot just graph the vertex and sketch in, or graph the x-intercepts and sketch, because I need all of these points to separate the non-examples to the examples. So I have to be exact with my graphing. It can't just be a sketch here. So since this could equal, I'm going to make it a solid line. Right? I'm going to make it a solid line. Whereas before, when I was solving in one variable, all I really cared about were my zeros of the function, so I could figure out when am I below, when am I above. I really didn't care about all of these other points. I really didn't care about where the vertex was. I just cared about which values gave me less than 0 and which values gave me greater than 0. So that is just a sketch. So sometimes we really need to know the difference. When are we just sketching the parabola, and when do we actually have to graph the parabola? So this would be a graph. So when am I less than or equal to? Again, if I plugged in 0, 0 in here, I would get 0. Plugged in 0 there, I would get negative 1/2 4 squared. This is all just going to be negative. So is 0 smaller than a negative? No, it's not. So it's again going to be less than or below the parabola. So that would be my solution set there. If it wasn't below and that was false, then it would be everything outside on that side. Let's try another one. Y is less than or equal to negative 2x squared plus 4x plus 1. Again, this is a parabola. We are going to graph y equals negative 2x squared plus 4x plus 1. In this case, I can't just factor and find the zeros because that would allow me to sketch. That would not allow me to graph. And when it's an inequality in two variables, I need the solution set on my graph with exact values. So when I need an actual graph and not a sketch, factoring is not enough. Just knowing the zeros and whether it opens up or down is not enough. So when you want an actual graph, you have to complete the square. So to get the vertex, we're going to factor the negative 2 out of the first two terms, divide by negative 2, divide by negative 2, push that 1 aside and leave a space. I'm going to complete the square. I'm going to take 2 divided by 2 is 1, 1 squared is 1. What did I really add? I really added negative 2 times 1. I really added negative 2, so I add 2 out there. Now I'm going to write it like this. X squared minus 2x plus 1 is now a perfect square, which can be written as two numbers that multiply to give 1 and add to give negative 2 squared, and then at the end plus 3. So now I have it in vertex form, and I know my vertex is 1, 3. And I know it opens down because it's negative, and since my a is 2, instead of going over 1 down 1, I go over 1 down twice 1. Instead of going over 2 down 4, I go over 2 down twice 4. And I'm off my graph, so then I'll stop at that point. Since it's less than or equal to, I will make it a solid line, not a dashed line. And now since it's less than or equal to, let's actually change this to greater than or equal to, because we haven't had that one yet. Let's change that to greater than or equal to. This one I'm not going to test 0, 0, because I can't really, actually no, I know 0, 0 is on the inside of it, right? Because when I have 0, it should be there. So it's on, let's test 0, 0 then. So when I plug in 0, I get 0 is greater than, all of that will wipe out to 0, all of that will wipe out to 0, and I have 1. Is 0 greater or equal to 1? No, it's not. 0 is not greater or equal to 1. Therefore, all of this is my solution set here, if I'm using greater than or equal to. And that would be my solution set. So basically, how is the solution of a quadratic inequality in two variables different from a quadratic inequality in one variable? The solution of a quadratic inequality in two variables is a set of ordered pairs, right? So it's all my x, y pairs that can be represented as a region. So that's why we have to graph it on a coordinate plane. The solution of a quadratic inequality in one variable is a set of numbers, right? X could be 5, or x could be 7, or x has to be between 5 and 7. That can be represented on a number line. So this would be my representation on a number line, making numbers up, where it could be like in between or something like that, right? So that's why all we have to do is we have to factor, find our zeros, and then sketch it out, right? Oh, it opens down. Oh, it falls between these two. When is it less than 0? Oh, it's less than 0 there, and it's less than 0 there, right? So that's what we did those last two classes. Or we can use our sign analysis or whatever. But factoring for one variable, when it's two variables, you have to complete the square. We have to put it in vertex form, right? X minus p plus q squared. We actually have to graph it, and we have to shade in something. So 2 variables versus 1 variable. Make sure you understand the difference. They're asking different things. All right, we have a satellite dish. It is 60 centimeters in diameter, so 60 centimeters across and 20 centimeters deep. The dish has a parabolic cross-section locating the vertex at the origin. So we are going to locate the vertex right here. So we have to create our xy axes. There's our xy axis, so the vertex of this parabola is at the origin. So we need to put in some important points. So 0, 0 is the vertex. If it's 60 centimeters wide and 20 centimeters deep, then that point right there will be 30, 20. This point right here would be negative 30, 20. So we have enough points that we can create the equation, because we know the parabola will be where we plug in P and Q, which is 0, 0, so we have y equals ax squared. P and Q are 0 because it's the origin. And now we choose a point, an xy pair, that we plug in to solve for a. So if I choose this point right here, I plug in 20 for y. I plug in 30 for x. I get 20 equals 900a. Divide both sides by 900. I get 20 over 900 equals a. Reduce it down, 1 over 45 equals a. So I have y equals 1 over 45x squared. That is the equation of the parabola. We want to, so now if I ask you, from what region can the dish receive a signal? Well, the dish can receive a signal anywhere on the inside. If it hits the edge of the parabola, it's not going to receive the signal. So it has to receive the signal anywhere inside. So it's anywhere greater than this, but not equal to, right? So anywhere greater than 1 over 45x squared is where all of those xy pairs, all of those locations on the grid will receive the signal from this satellite dish. Anywhere out here will not receive a signal from this satellite dish. To that satellite dish. All right, let's look at this one. Again, I could give you a graph, a parabola. I could give you the shading as above this parabola or greater than this parabola but not equal to, but I need to know the equation of the parabola to be able to complete. So whenever you're given the vertex and a point, you can find the equation to the parabola. To find the equation to the parabola, you would go y equals a, plug in your vertex, x minus 2 squared plus 4. Now I'm going to borrow a point along my parabola, 3, 2. I'm going to put 2 in place of y. I'm going to put 3 in place of x, and I'm going to solve for a. 3 minus 2 is 1, 1 squared is 1. I'm going to subtract 4 from both sides, and I get a to be negative 2. So I have y is greater than, not equal to because it's dashed, negative 2 x minus 2 squared plus 4. Right? I could expand all that out and change it to general form, or I could just leave it like this in vertex form. That is the equation to this solution set. So if I ask the same exact question, but I only shaded above the x-axis, so this shading happens only positive values of y, so nothing below. So how can I say this is my solution set, but all of the stuff, so this time instead of greater than, we would use a less than. We definitely can see that. So how can I say, well, I don't want all of that stuff below? So I start off with y is less than negative 2, because I already found the equation earlier, x minus 2 squared plus 4. But now we need to figure out how can I restrict my domain so that only uses the x's between this location and this location. So my x value has to be between a and b, greater than a and less than b, because all of those x's are producing positive y's. Any x less than A or any x less than B is producing negative ones, negative y values, and I don't want those. So this is where we would solve for x. In other words, my y equals 0. So if 0 is y, we can find x. And how do we solve an equation? A quadratic equation? We could solve by factoring. We could solve by graphing. That doesn't help. I don't see those exact values unless I type that into Desmos or some kind of technology to graph it for me. Or I could solve it by square rooting. Since it's in vertex form, the square rooting works out nicely. So I just isolate the x minus 2 squared by subtracting 4 to both sides. I divide both sides by negative 2. I square root both sides. Don't forget, when you square root both sides, you get the plus or minus of root 2. Right? And now I'm going to isolate, so I'm doing BEDMAS backwards, brackets last, right? And now I'm going to add 2 to both sides. So I'm going to get 2 plus or minus root 2 is equal to x. So B is going to be 2 plus root 2. A is going to be 2 minus root 2, right? And x has to be between those two. So if I restrict my domain and say that only these x's are allowed, I now have graphed only the part underneath the graph, stopping where y is greater than or equal to 0. If it could equal 0, then I would include the equal to signs, right? So if it's allowed to equal 0, then I would put the equal to signs, right? Because it says less than this, but not equal to it, but it could actually equal 0, then I would include those. But since it doesn't, I'm not going to include them. There we go. Question like this, a rope of diameter d centimeters can hold up to m pounds modeled by this inequality. Graph the inequality. When I say graph, yes, I need an exact graph. I need to see the detail to it. But if the numbers are so big, I'm not going to expect you to be counting out, go over 1 up to 100. A sketch like this with enough important information would be good enough. For example, I can see that my vertex is 1, 0. I plotted that. There's 1, 0. Since A is 200, when I go to the right one, I go up 200. So this would be 2, 200. This would be 0, 200. So I have enough information there without actually having to use like a scale and a graph. That's okay. The number's so big, I wouldn't expect you to have to do that. All right, so last lesson in this chapter, graphing quadratic inequalities in 2 variables.